ask that question because you both rather nicely answered them in your talk. So I think...
Can you summarize them?
That's mean. I suppose that in response to the scaly comment, is it? Right. Summarize it. So, yeah, okay, sure. I will try to summarize it. So, Bill, as I understand it from your talk, we all agree biodiversity is actually rather more complex than non-biodiversity people think. I suspect that's the case for any one of the subdisciplines, that those of us working outside of the subdiscipline think, all right, well, it's soil, it's more or less the same thing, carbon, more or less the same thing, people, more or less the same thing, biodiversity, more or less the same thing, and then you break it apart and it's horribly complicated. But for biodiversity, we've got all kinds of issues about species and scaling relationships and occupancy of things, which complicate matters, including biodiversity offsets. So more so perhaps than we had initially thought before Bill's, I thought, excellent talk. So that's the big challenge. I guess, how do we distill that complexity into something that's useful?
I guess my simpler still version is essentially a reformulation of the questions that were asked from the audience, which is, if we know that it's such a complicated currency, how do we turn it into something we can manage for? How can we turn it into something that we can, if we're for instance coming up with a scheme that involves payment for outcomes, what's the outcome that we're going to measure, that we can measure? If we're going to do something which is a more classical form of payment for some form of management, what sort of management do we actually believe will deliver something which is meaningfully and usefully reflecting biodiversity in a way that provides a public good? Because ultimately, the argument for all of this stuff is payment for a public good. And if what we're paying for isn't providing a public good, then maybe we shouldn't call it biodiversity.
As Bill has done so much better a job than I've done, I'm going to let Justin summarize his own talk as well.
I'm not sure I can remember what I said. So in a similar kind of vein, I guess, I think we made a lot of progress in finding the data, finding new sources of data, higher resolution data, which is really helping a lot. And we've made a lot of progress in how we kind of model and maybe integrate these two things together, but not done a really good job, at least from the community that I work with, in trying to understand how we use those models and that information to make better decisions. And of course, there's a gap between the kind of physical scientists trying to understand their models and data and the decision makers and how they make their decisions, of course. But that's it's also a gap in trying to understand the utility or the usefulness of that information as well. So we can produce soil moisture at 30-meter resolution across the whole world or whatever, but is that actually very useful for making any kind of decisions if we can make a decision? So I think that's a bit of a challenge that cuts across the disciplines almost. I think there's lots of new exciting opportunities to use new data that's going to give us better understanding of the physical processes. I think we can use this to try and understand kind of spatial trade-offs as well. So if we're making decisions at the scale of the farmer, but we're also making decisions at the scale of the basin, and they can be in conflict, then can we actually use these models to try to understand those trade-offs and actually have better outcomes all around? I'm not sure whether that was really on my conclusion slide, but that's what I'm thinking of right at the moment.
I guess cutting across the scale piece, I think we have this question of, to what degree do things, I guess, can we understand things like scale, well, for root of another word, scaling rules, or issues of fractalness to improve our predictive models, to overcome some of these issues? To me, that seems like a fairly fundamental, probably mathy challenge that cuts across both disciplines and probably all of these sorts of disciplines. I guess from now we'll take if there's comments, questions from the audience. Gentleman in the back.
So, decisions really involve intervention, and before you intervene, you really have to have a causal model so that you know what's going to happen. So, I didn't hear the word causal model yet this morning. So, do you have those sort of instrumental causal models where you can sort of if you intervene. I noticed that counterfactual was on the first set of notes, so which you sort of need to build a causal model. So maybe a word on that would help.
I think from the kind of hydrological prediction or water resources management angle, I mean, the models themselves are the causal models. If you change something, something happens, and you can use the models to kind of do that. You know, you can put a reservoir in, you can put flood defenses in, you can change the way you manage the land, and you will see a response in the model. Of course, there's a whole bunch of caveats there about how you actually model those interventions and the impacts and so on. And it gets pretty complicated, because if you're doing something at one part of the catchment, it's going to affect locally, but also downstream as well. So there's lots of complications there. So I think the models are there, but we either can't characterize those interventions very well yet, I think, and we don't really know how those interventions propagate through the system very well either. Maybe that's because we don't have the understanding, the time, the funding, or whatever, I don't know, but I think it needs to be done. Often it's done in, like many things, it's done in isolation. So here's my intervention, here's my effect that I'm interested in, and you don't tend to think too much about all the other stuff that's going on. But that becomes a very high-dimensional problem, which you might end up looking at in brute force methods by running, you know, tens of thousands of simulations with your model to try and understand the complete space of impacts given your uncertainty in the interventions and how those interventions propagate.
In terms of causal models for some of these biodiversity conservation issues, there are the starts of them. As much as the currency itself is complicated, the processes involved are relatively simple causal chains. The species have to get to a place, they have to be able to make a living there, they have to not go extinct. And there are a series of essentially process-based models that are about patch colonization, patch occupancy, patch extinction, that and using those then to try to inform where habitat restoration might best be done, and the parameters are relatively finite in terms of dispersal kernels and that sort of thing. The problem is that people tend. There are also good process-based causal models for how habitats change over time. And succession is reasonably well understood. That doesn't tend to get incorporated into these models, and could be. At which point, then that would help build the other half of the legs, because the legs ultimately are down to either the processes of colonization and extinction or the processes of becoming suitable habitat in the first place. I think those could be integrated pretty easily, but they're not often.
There's a question in the back. Someone else raised their hand before? Oh, I've forgotten. Lady in the back, the green.
Okay, Jess Davis, Lancaster University. I think a point that was shared between both of your talks was it was about scaling for what purpose was something that's important. And I think Justin, at the end, you cited a paper that was scaling, and they were trying to get the same answer from a scaled result. But it's kind of, we need to think about what bits of the answer that we need when we're scaling. So we need to think about what behaviours and parts of the response that we wish to retain based on the decision we're going to make, or whether it's interconnecting with other processes. And I sort of wondered whether you felt that in your community, were we doing a good enough job in terms of defining what we need to retain from the response when we scale, and could we do a better job of that?
So I'm not sure what you mean by my community. As pure hydrologists, I don't know if pure hydrologists think about decisions. I don't know. I mean, I cut across a few other communities in terms of people interested in hazard mitigation, droughts, floods, food security, energy security, and so on, which makes it interesting, because then you are thinking not about one decision or one part of the upscaling process that you're interested in, but many, and they all operate at different scales. And I think that's the fascinating thing and the real challenge, and it's similar to my last answer about trying to think about all of these things at the same time. Not sure that answers your question. I'm just saying that to understand water and how it upscales, it affects so many things that it's a huge challenge, but makes it really interesting as well.
I guess the other thing I'd add to that is that there isn't one scale of policy. There are local councils, there are regional bodies, there are national bodies, there are continental governments and governance, and to a certain extent global governance, and they will be creating policy at different scales. And even within those, sometimes there may be things that they care about which are at finer scales than those. So I was actually thinking in terms of the hydrological work. It might be that once you start having these 30-meter resolution things, you can start drilling down to the point that actually the poor farmers are under water stress, even though this region, this catchment has got lots of water. All the smallholders are the ones that have drought stress, and so that then informs a policy which is saying we need to find ways to aid irrigation for the people who can't afford to put in the infrastructure themselves, or something of that sort. There may be even larger scale decision-making processes may care about small scale information.
Just one example that I think is kind of sums up a lot of these issues is the building of dams, especially large infrastructure, large dams, where you're moving people around. That has lots of social implications. You are affecting biodiversity, you're affecting the landscape, all kinds of things, and is driven by many kind of top-down decision making, and you end up with like very bizarre things happening that, small-scale farmers get moved from where the reservoir is going to be to downstream. They're given more land, but they end up being poorer because the reservoir is now stopping the seasonal flooding. So, there's lots of these ideas about trade-offs and things just basically being having very bad outcomes for the poorest of society. I'm working with people in Manchester who've been, for example, they were working with the government of Congo to actually look at how to build a dam in a better way, thinking about all these other impacts. So how does it affect the smallholder farmers? How does it affect the orangutans? How does it affect everything? And so they did all these kind of multi-model, coupled model simulations to say, across all these different metrics, how much power are we producing, which is the most important thing from the hydroelectric, how many orangutans are we displacing, how is food security going down, and so on and so on. And you can actually see there's good trade-offs. You can actually see that there are some options that are much better for many different things. Now, of course, you give that to the government and they ignore it and they go and build the giant dam anyway, so it doesn't really matter. But there are tools out there that you can start to think about different processes and different stakeholders at different scales and actually come up with better solutions that cut across all these different interests.
So I was just going to say, was your question, just to rephrase the question, were you asking the question is that are we getting the responses right? Are we thinking carefully about what our response is when we...
I was thinking about scaling models.
Right.
That then when we're upscaling or downscaling models and we're going to use them for some purpose, we need to be ensuring that we're capturing the bits of the behavior of the model that we're interested in. So an example, I think it was quite nicely demonstrated by just his examples actually about flooding and water availability for farming. Those are two different parts of the response of a hydrological model.
Right.
So when we're moving between scales of models, we don't need all the behavior, we only sometimes need some of it.
Okay.
And if I was wondering if we need a better formalization of what parts of the response, what definition of biodiversity do we need for this type of decision? Because that can help inform how we then use and scale a tool.
Right. I think that is actually a really central question, and we had a bit of a discussion about this last night. That to me it seems that given we have the world is so interlinked that you almost need to sit down if you're going to do any kind of major infrastructure or natural capital decision and say, all right, this thing we sit in, does it have some sort of global significance? So do you have a globally important peatland? Do you have a globally important piece of biodiversity? If so, obviously that needs to be considered. Then you go to the national scale. So nationally, is this, really important farmland, really important, is the Peak District really important for so then that needs to be considered. And then finally you go down to the regional and local drive and say, well, what do people actually want locally from this landscape? In some cases, you may not have to worry about these scale disconnects because it may just be local things that are interesting. And in a national or global context, other stuff, non-local stuff, isn't that important, which simplifies it. But I think that's almost the process one has to take, at least, if not from modeling, at least conceptually thinking these things through. So I would completely agree with that. So Peter Cox was next, I think.
So thank you both for very interesting talks, first of all. What you both seem to show was that we live in this time where we've got probably an unprecedented amount of information and spatial patterns. Generally from remote sensing, particularly Justin's stuff, lots of remote sensing, and short records. And yet we're often interested in the temporal change. What's the direction of travel? And I could see, you showed these interesting things, Bill, where an expanding species has a sort of clustered pattern and a declining species looks much more patchy. And I could see also in your fantastic movie, Justin, that the dry down processes and the wet up processes have different spatial patterns. So my question is really, is there a hope, is there a chance here that we can get, what's commonly called a space to time kind of transformation by looking at spatial patterns to understand temporal dynamics, even when we don't have a long enough time scale for the records? Are there generic things that we can take out of these systems about space to time, basically?
I guess to a certain extent, what we found was that you can use spatial patterning to identify recent dynamics.
Yeah.
So that it wasn't just that it wasn't just that we could use spatial pattern. Sorry, it wasn't just that we could use past performance to predict spatial pattern, but we could also use then spatial pattern in a different data set from Belgium to then infer which of these species had declined or increased in the past. And so yes, the answer basically you can use pattern to predict unseen past dynamics. But with substantial error bars and all these questions about uncertainty of modeling apply here. There were plenty of species that you would have misforecast, but most of them we got right.
I think there's a lot of value in trying to combine data in some way, the kind of trade-off space-time, basically getting more data, looking at more locations, getting more samples, characterizing the extremes better is good. I think thinking about the longer term trends as well, we need to not really get kind of put out of place by thinking about just remote sensing, because it's all great and fancy or whatever, and we want to do things at very high resolution with the latest sensors and products, but we really still need to be thinking about the very long term, hundreds or even thousands of years, and trying to mine some of the great records that do exist for those that are different from what we are experiencing right now. I know you do climate science, so this is stuff that you think about all the time. How representative are the data sets that we have now of the types of states that we could exist in? And looking at the last 30 or 40 years is really not representative, and it's not even representative of the last 100 years because of longer term decadal climate variations. So so personally speaking, I think remote sensing fantastic, new sensors fantastic, but they really don't give you the temporal scale that you should be thinking about as well, especially when we're thinking about moving from different states as well.
I think John Deering was next. Sorry, John.
Thanks, Felix. So my question is somewhat related to that. It's considering the kind of higher level properties of a complex system, which you're both studying. To what extent does scale, or how much understanding do we have of how scale intersects with those properties of a complex system, like resilience or the likelihood of collapsing? Those seem to me to be quite important aspects of scale. I just wondered whether you feel that we're close to getting a kind of good understanding of these generic properties of complex systems.
Are you giving a talk on this later? Okay.
Damn.
I was going to say our answer afterwards, after you've given the talk. Are you going to say something?
I've certainly seen some papers suggesting, not at the very coarse scales, but at fine scales, that some of this spatial patterning stuff can be among the symptoms you look for systems close to a tipping point. That there are shifts in the clumpiness or diffusion of the vegetation patterns or the population patterns or whatever. At the coarser scales, I'm not sure. It's a good question, but what I've heard about, and even that I'm not entirely convinced by yet, is work being done on very fine scales. And maybe that's a typical problem in general of ecology, is people work at fine scales because that's what they can do.
What do you mean by fine scales?
I mean tens of square meters, hundreds of square meters, maybe. Yeah. So in these, you're often looking at an area of a few hundred square meters at a resolution of a meter or two, and at that sort of resolution, there is some evidence of using this sort of scaling behavior as a symptom of systems under stress. But
I'm afraid we don't want to eat into the next session's time, so I think we better leave any more questions for lunch. And do we have another drinks reception today?
I don't know.
We have dinner. Right, but
We're all at dinner today.
all for dinner today. So I think hopefully there'll be more time for talking with our speakers. And yeah, again, thank you very much both.
yeah, I'm off to my.
Oh,
It's my son's graduation. I'm off to Durham.
Bill's off. So
I'll be back Monday.
right. So yeah, thanks again for excellent.